Hello, good morning, everyone. Thank you for being with us this morning for our webinar about the future role of hydrogen from a national and European perspective. So before starting, I'm just quickly going to go through the different options that you have on the right side of your screen on Livestorm. So firstly, you have the chat box where you can say basically anything you want, any remarks, any thoughts that you have during the presentation. Do not hesitate. We also have the questions options, so that's where you can ask any question. And well, please ask the questions in this box rather than the chat box, so that we try to answer to all of them after the presentations. And finally, you also have the polls that will go and that you will find throughout the webinar, and new polls will be added, and you do not hesitate to answer. That would be great. I'm also quickly gonna go through the agenda of today's presentation. So firstly, Peter Birkner is gonna talk about House of Energy, and he's gonna make a little introduction. Also gonna talk about the consideration on the role of hydrogen in energy transition. And then we'll have a questions and answers section as well. And then Geert Meulenbelt will talk about DCbrain, about how a French startup supports the hydrogen strategy. And we'll talk as well about Fluxes use case. And then again, a question and answers section. So I will now let Peter speak first. I will add his presentation. Okay. So Peter, whenever you want.
Thank you very much, Maureen, and a very warm welcome to everybody who is joining our webinar. Et bien sûr, bonjour cordial pour la francophonie. I know that we have quite some guests from France, and just one personal remark. France is one of my favorite countries, and I just had the opportunity to spend 2 weeks of vacation in this great country. But I have to talk not about holiday and vacation. I have to talk about the House of Energy and the considerations on the role of hydrogen in the energy transition. I'm an honorary professor at the Bergische Universität Wuppertal, and I'm managing director of the House of Energy. And just to explain you in a nutshell what this institution is, it's a think tank which is working in a transdisciplinary way. So we are bringing together people with different background from economy, policy, and science. Mostly, we discuss energy-related issues with the economy, and the companies want to do something new. They have ideas, but there's always a small gap in order to make this product, which has to be energy-related, ready for the market. And this little gap we try to bridge with science. So we design projects with a economic importance, but also with a scientific relevance. And those projects are supported by policy, above all our regional government of the federal state of Hesse. In the meantime, we have projects in Germany, but of course in our state, but also in Europe. We are a team of 15 people, and we are sitting on the so-called Science Park, which is an incubator in the city of Kassel, which is halfway between Frankfurt and Berlin. Just to tell you how we are thinking, and we try to understand the new energy system in a holistic way. And so from this point of understanding how the energy supply will work tomorrow, we can deduct the requirements. And technology is creating options. So requirements and options. And technology, from our point, is based on materials, and also recycling is a part of the whole story. Next to technology, we have to look on the legal framework, because this is defining feasibility and economy. In a nutshell, it's defining the business case. You have to look at finance. You have to look at the acceptance of people. And last but not least, you have to make sure that there is appropriate education at the universities. So this means we have companies in our membership which are representing all elements of the new energy system. That's in a nutshell. If you want to know more, just visit our homepage. I have to say that so far everything is in German language. So this is one of the to-dos we still have to make it more international. But now let's talk in a very holistic way how this energy system of the future would look like. It will be based on renewables. And to start with, it's not an issue of quantity. There is enough energy coming from the sun. And one pioneer of this new energy strategy, Joachim Nitsch, calculated that per day, 20,000 times the energy we need is available on this planet Earth. However, the issue is the quality of the energy. It is low density energy, it's volatile, it's intermittent, and the availability is very, very limited. And this brings us to two challenges. The first one is power. We have to establish a huge power, huge capacity in order to harvest enough energy. And of course, we also have to stabilize the whole thing. So this leads us to the second issue, it's space and surface. We need a lot of space in order to establish the infrastructure. The space has to be available. We need the acceptance of the people. And not to forget, we also have to look at biodiversity. Now, I would like to show you the situation of Germany. We have a demand maximum plus minus 100 gigawatt. And in the past, we also had 100 gigawatt capacity of power plants. And now I'm talking about the electricity sector. And answering the question, what is the capacity to be installed in Germany in order to get 600 terawatt hours, which is more or less our annual demand in the electricity sector, done by a more or less renewable-based system? The answer is we have to install a capacity which is 4 times higher than the capacity was in times of fossil fuel-based power plants. However, the positive news is that renewable energy sources are not working all together at the same time. So even if we have to install 400 gigawatt, we will observe in the grid only 200 gigawatt. This is due to diversity. Sun is not shining at night, but wind prefers to blow during the night. So to establish 400 gigawatt, and we have to control and to work with 200. Now, this is only 50% of the truth, because if you just focus on electricity, this will not allow us to fulfill our CO2 reduction targets. It will even not be economic. So what we have to do is we have to take also the heat and cooling sector and the mobility sector into consideration, and we have to make everything more electric, because the electrical energy is extremely efficient. And this efficiency is the second column next to renewables in order to get a new system. Here I have the bars, which I showed you before, but I have it now for the whole energy system. The electricity is 600 terawatt hours per year. And if I add mobility and heat, then I need 2,500 terawatt hours per year. And if I just do an extrapolation to say, okay, for 600 terawatt hours, I need 400 gigawatt, then I need more than 1,600 gigawatt if I want to compensate or to supply the 2,500 terawatt hours for mobility, heat, and electricity. So this means where I have one wind generator today, I would need 17. Or one solar panel, I would need 17. And you see that this is not a such good idea. So efficiency and sufficiency is also very, very important. So we calculated that we need a reduction of the energy demand by some 40%, which brings us down to 1,500 terawatt hours, which still means we have to establish something like 1,000 gigawatt, which is 10 times the capacity we had in the past. But this is an issue which is at least feasible. And of course, we also have to think about the role of imports. Again, this is the figures of Germany, and you have to do the same consideration for all other countries. If you have a country that has, for example, double time of sunshine compared to Germany, you get much more energy out of the same solar panel than we have it here. So this makes that you should think about a European solution and not just putting 10 times the capacity compared to the fossil power plant area here in Germany. What I said, I can transfer into a 4-step strategic way down the road how to establish this new energy system. The first step is to have an extensive approach, not just electricity. It's good, it's fine, we need it. It's a central energy element, but we also have to integrate mobility, heating, and cooling. Second, we have to reduce the challenge. We have to minimize demand. So this means without efficiency and sufficiency, it will be not possible to get a technically feasible system. And of course, the remaining challenge we have to control, and now we are talking about all those smart elements, smart grids. We talk about sectors coupling, and here the hydrogen comes in. And as well, in the case of reduction of the challenge, as in the step 3, controlling the challenge, digitalization plays an important role. Digitalization allows us to identify where we can reduce the energy demand, and digitalization allows us to control and to stabilize the whole thing. And finally, when I have all the data, I can think about new data, new business opportunities, starting with augmented reality, continuing with process optimization or predictive maintenance and many other things. Again, that's just in a nutshell. But when power is the issue, this means we need huge infrastructure. We have to minimize the infrastructure in order to get it cost efficient. Now, two specific issues. I defined the economy of miniaturization. I'm sure that most of you know the economy of scale, the bigger the better. And now we have a new law, and I can tell you that the price for renewables and all the other infrastructure elements will further go down. On the opposite, the costs of big power plants will increase. So even from an economic point of view, it makes absolutely sense to go to renewables. I already talked about digitalization. I do not want to go into detail, but this decentralized and small system with a lot of power plants needs to be coordinated, and coordination means to collect data, to use data. And so digitalization is a must, a prerequisite for the new energy system that is based on renewables. Now, coming slowly a bit closer to hydrogen. Hydrogen is very inefficient compared to electricity. However, efficiency is important, but it's not everything. You can be very efficient, but you can be also very, but you also can have a very low effectiveness. For example, if you have a bus or a truck and you drive it electrically, it will be super efficient. However, if the battery needs all the space you have, it will not be very effective because you don't get any people in. And now this means there are some limits, some technical limits with the electricity. And then we have to step over to hydrogen to be less efficient, but much more effective. And when it comes to ships or to planes, I think we also need benzene or kerosene. And we don't have to start with kerosene, with synthetic kerosene. We can start with electrons and add hydrogen. And the borderlines, which application you fix with which energy carrier, are not clear yet. For example, I heard that Airbus now thinks about planes fueled by hydrogen. I heard other opinions that no, hydrogen will not work, it's kerosene. So there is technical development, and we have to be careful when investing money and to be aware of the risk. So this is a very holistic picture where it can go, but whether trains or ships will be driven, if there is no overhead line for trains, by hydrogen, or whether it will be benzene, I cannot tell you right now. This is a question of the technical development. Hydrogen in general, we can use it for mobility. This is what I was talking about. We also will need it for heating. I think it's very hard to get rid of all the gas-fired heating system in domestic or residential houses. So I think quite a whole number of buildings will be heated by hydrogen in the future. Hydrogen is a base material for chemistry. We can use it for steel industry. And not to forget, we also need some controllable backup generation in electricity. What are the sources of hydrogen? We can do electrolysis, centralized, close to North Sea, for example, to connect it to offshore. We can do it decentralized, to have these modular systems. Hydrogen is also produced in chemical industry, for example, as a byproduct of chlor-alkali electrolysis. Hydrogen can also be produced by using natural gas, but then of course we have the CO2 issue, so we need CCS. And not to forget, we also can import hydrogen. And maybe you also should think about this import issue. If you do not import any gas into Europe, I know that there's a big political discussion, but I'm not sure whether we are interested in a very destabilized Russia. So maybe we take some hydrogen in future from them and not natural gas or oil. But this is a political issue. I know that I shall slowly finish, and I have 2 slides. So I think from a timing point of view, it's still okay. Here I have some figures, what a 20% replacement of natural gas by hydrogen means for Germany. I just can tell you that we need about 1,900 terawatt hours hydrogen, which is quite some volume. And if I assume a 75% efficiency of the electrolysis, This means that we have to establish either 250 gigawatt photovoltaics or 100 gigawatt wind generation. And at the moment, we have something like 50 gigawatt photovoltaics and 55 gigawatt of wind generation. So this means in order to get 20% of the natural gas from an energy point of view replaced by hydrogen, we have to establish 5 times the photovoltaic capacity we have today, or we have to double our wind generation capacity. These are big figures, and my conclusion is that we can do something in Germany, but import of hydrogen will also play a role. And what's also an interesting figure, if we use natural gas as the base material in order to produce hydrogen, we only need 1/7, 6.5 is the correct figure, of energy compared to electrolysis. In a nutshell, it's a challenge to get the requested volume of hydrogen, but it's feasible at least on a European level. My last slide is a bit high level, and the question is how to get this whole story, which I just described very, very briefly. And you can imagine that you can talk about this for hours, but that is not what we want to do. What are the foundations we can build on? So we need a lot of capital, but capital is available. Also, technology is largely available. We have to improve some components. We have to further develop. We have to scale it up. But capital and technology is available. The shortage is time. The climate change is advancing very rapidly. So time is our challenge. So what we have to do is to bring the capital to the position that it's invested in the right projects in order to get the technology what we need in order to establish such a system, which again I described for Germany, and based on the principle of subsidiarity, of course it will be different in other countries. We have to get the right allocation of externalities. So who is producing costs on the expenses of third parties has to pay for it, CO2 price, and we have to guide the financial flows to sustainable investments. Let me finish with the statement that we have quite some coal-fired power plant projects on this planet Earth, but 50% of them are on hold because nobody wants to invest in them. And I think that is the way how we should manage this transformation. It's not a German thing, it's not a European thing, it's a global thing. Thank you very much for your attention, and I'm sorry that I guided you a bit fast through the whole landscape of this energy transformation process. Thank you.
Well, thank you very much, Peter, for your presentation. If you have any questions, feel free to ask them on the right side in the question tag. Don't worry if the questions come up a bit later, we can always answer them at the end. So we have a question from Nicholas for you, Peter, which is where would you import the hydrogen from, assuming you want to buy green hydrogen, of course?
That's a very, very good question with a high political relevance. Just considering the amount of hydrogen we need in order to have an impact on the economy, of course, in the long run, it could be green hydrogen produced by green electricity. So my first statement would be that for a transition period, for an interim period, we also should use natural gas in order to produce hydrogen. Either we import the natural gas and do the production here in Europe/Germany, or we directly import hydrogen from Russia or from Russia, or from if you take it liquid, also from Iceland. In the long run, I would say North Africa plays an important role for the hydrogen supply of Europe, and of course also the southern parts of the European Union. So now I talk about parts of France, Spain, Italy, because there's much more sun compared to Germany, and the result is that it's cheaper than producing it here in Germany. However, we also should take into consideration all those offshore wind farms in North Sea. So it's a multiple solution, and depending on the time.
Okay, well, thank you. Maybe we'll continue. So I'll let Geert speak now.
Thank you very much.
So, good morning, everyone. Herzlich willkommen to our deutsche Freunde. So my name is Geert Meulenbelt, and I'm actually kind of a European, born in Holland, and now for over 20 years. I have a connection problem. I'm not sure if you hear me. It's not working on my side. My connection has been restored. I hope you still hear me. Let me know. So I was telling you that I'm here from a European perspective, being Dutch and raised and lived a long time here in France, and happy to work for DCbrain, and mainly involved in an international collaboration. So what I would like to talk to you firstly is about the perspective as we see it, and particularly in the gas market, which is an important driver for hydrogen. But agreeing totally with Peter, it's a very broad perspective that we should take into account. It's not only about gas networks, it's also about mobility. And what we see in the gas networks, the fact that hydrogen is coming in and renewable energies, there's a common problem that the inflow is not very regular, and you can well imagine if you think about solar or wind energy, and that's an issue for the operators. We see also there are tools often used, tools that have a certain age, 10, 20 years, that may be very, very powerful, but they're not really the digital solutions that we would need to solve that uncertainty type of problems. We also see that many companies have invested in data lakes and data science teams, everything around data, but at the end of the day, it's still very, very difficult to get value out of the data. And finally, we see that customers become even more important. It's not a customer who will accept a 20-year contract and will never complain. It's everything is going much more dynamic. So what we did at DCbrain, we built a solution, and we've been doing so for over 5 years now, and this is called Intelligent Network Solution. And the idea is that we need to digitalize the networks and to understand and optimize them. And even though in many occasions the data we have at our disposition is not fully complete. And the second thing is it should be really easy to use from an operational perspective. So there's no code. It should be really a tool to make decisions on an operational level, and it's not for smart, expensive data scientists. And the operational aspect is really very important because the context is changing dynamically, hourly, a quarter of an hour, and the solutions must be compatible with that frequency. So just to show a little bit what the solution, how we build that up, it starts with bringing in two kinds of data sources. And the first data source is the topology of your network, the assets of your network. In a gas context, that can be, if you're a transporter, the compressors, you have the valves, you have where the gas comes in, where the gas goes out, and that can be put on a map, and we call that topology. And they often come from specific information systems. At the same time, you have the information on the flows. What is the pressure? What is the outside temperature? How does the gas flow through the network? And the basic idea of INES is to bring those two sources together in the single user interface. And you think that's maybe easy, but the reality is that that's very, very, very complex to do that, because in many times the traditional data systems that incomplete, so you already spent quite a lot of time to put that in order and to get the right information in the right place. But when you do that, you can see your network, and we call this asset mining. You can see the flows, you can see the customer, and this gives you already a first level of information. But it's the kind of the building block on top of everything is built up. So going a little bit more into the details, from that information you can analyze on a given point on a network what goes in, what goes out. In the gas world, we call this the balance of the gas. And very easily, very graphically, you can analyze where the gas comes from and where it's moving to. And identify losses, which can be purely network-related losses, but you also have what they call non-typical losses, or it can be even theft or things that happen typically in distribution networks of energy in global. Then a third level, and now it's getting more and more interesting and also more relevant for the hydrogen, is the tracking and forecasting of energy in a network. We have seen in the past that biogas is a new form of clean and green gas energy, and it's important for a part, at least, of the customers to know where the gas comes from. So what needs to be done is to track in the network how this gas will flow. And that's a really challenge, and even more so with hydrogen, because hydrogen has a kind of specific characteristic. It requires a lot more volume to produce the same amount of energy. About 3 times more gas volume is needed to produce the same energy for an end user. And that has a consequence that existing gas networks has a great difficulty to cope with that. And the targets that are set for hydrogen in traditional gas networks, it's often around 2%. So you can think that's not a big amount, 2%, but you have to understand that this is an average, and if you add on 2% over a whole year, then you see very, very substantial amounts of hydrogen that can be mixed in traditional gas reactors, together with natural gas, together with biogas. And that mix needs to be forecasted, because the irregular inflows of renewable energy generated gas, it has a big impact on final customers. So maybe on a summer day, this actual percentage of hydrogen may be much higher than 2%. It could be even 20, it could be even 50%. And in that case, it has a big impact physically on the assets, and there must be some thresholds defined on top of which the hydrogen component should not pass, because otherwise it will harm the assets and reduce the lifetime. So there's a big it's not an easy way of assessing the problem. Digital solution is really helpful here. So when you do that, there's another when you build a kind of model from the network, we call this a digital twin, and from that you can do simulations. You can open a valve between two networks and then simulate what will happen. You can simulate on a very cold day with a lot of demand what will happen, and this really helps to do planning, to make important decisions on how the network will evolve over time. And hydrogen is a highly uncertain component. We don't really know how much will be generated, how it behaves, because it's very, very new. So this simulation is a really strong requirement from gas operators, both transportation but also distribution networks. And at the end of the day, what is most important, what generates the most value, is the optimization. And for transportation companies, this is optimization on how their compressors should be operated, how they should be fine-tuned, in what sequence they should be put, and this can generate a lot of savings on operational costs. When we look more at distribution networks, there's a lot about predictive maintenance. How do you optimize different equipments, different teams, etc.? These are often tailor-made optimization solutions, need to be designed, so it's a little bit higher investment than the others, but can be much more automated. So that's a quick high-level introduction. Some visualizations you can see here. The digital twin can be displayed as a network with some dots and lines in between, but also on a map, so you can see the different components, the different assets, alongside some statistics and a lot of different settings, not only embedded in the application, but also with an API to be used in traditional business intelligence tools that in many cases are already there. So that's a first part of the presentation. I'm looking at the time. It's still fairly okay. The second part is about the political and business climate. We have all seen that Germany took the lead on a 9 billion program on hydrogen. France, up to now, there was quite some activity in the industrial space, and it's probably good to underline that Alstom delivered its first hydrogen train in Germany. Air Liquide is a world leader, but not in the green hydrogen, but more in the gray hydrogen. But there's a lot of know-how in that company as well. We have plans for a fuel cell plant by a company called HDF, which is a conglomerate with different shareholders in Bordeaux, in the south of France. All in all, with quite modest public support. About 100 million was the budget we had during the last couple of years. Then Gemini came along with the big boost last June, and yeah, we can say France couldn't stay behind. So there was a decision about a 7.2 billion support plan, which both goes to supply measures and demand stimulation measures, and will be mostly focused on heavy industry and transportation. And France being France, nuclear energy is also part of the equation. And again, you can always look at different angles to this. When I was young, there were huge demonstrations against nuclear energy where I lived in Holland at that time. From a carbon perspective, right now, it may be a much better thing to have a nuclear non-CO2 emitting energy source instead of a coal-fired plant. knowing that anyway there's a 60% of all energy in France is generated by nuclear. So that's a given fact. This is part of the overall equation. The good thing is, though, that we feel there's a strong drive to collaborate between the different countries with really high-level negotiations and alignments taking place on a political level, which is much harder to get to the level where we here are, but we really expect there's going to be an increase, a boost in collaboration between the two largest economies in Europe, which could drive a lot of more activities in all the other countries. So I finalized my presentation with a use case on Fluxes, which is one of the partnership we have been able to set up. So Fluxes is a Belgian transportation company of gas. The challenge there's a plan for a new hydrogen wind-powered plan at the coast of Belgium, which is supposed to be able to start in 2023. There's still quite a few uncertainties on when it will actually start operating. This plant will deliver energy to mobility purposes. That's the main goal, but the excess energy will be deployed in the network, the Fluxes transportation network, and that's going to have very big consequences because it's really going to be important to know when and where the gas mix, how it will evolve over time, and the quality of the gas or the mix of the gas, how to track that is becoming really, really important. And you can do that in a physical way by installing what they call chromatographs. And these need to be replaced when hydrogen comes in the network, and that has a huge cost. So the idea is to try to doing that in a digital way, and that's why we started to work together on that topic. So basically, you need to understand there are two families of products applications here. One is the traditional way of working. We call it hydraulic simulation tools, which have been around for a very, very long time, and they kind of build up the model of the network step by step, pipe by pipe, valve by valve, from the bottom up, and that takes generally a very long time. And to align every team, it was estimated that might take up to 2 years to do that. And 2 years is a long time. It used to be okay when the future was predictable, but now in the new, more dynamic environment gas operators are living, this is becoming a challenge. So there is an alternative of doing things quickly, more quickly, and a data-driven digital approach is something which can be really, really powerful. And that's why we started to work together. So there were several phases. Like anywhere, it's really important to align the data, what we call a data audit, especially if you bring the two sources together, the flow information, the consumption information, that's often invoice information, it's most of the time of good value, but it should be matched with the identifications of all the assets. And even though the information systems have been there around for a long time, they were not really designed to make that connection. So it always takes a little bit of weeks to get that connection together. And then what we're doing right now is what we call the state reconstruction. So we make the digital model of the network, and we can design the propagation of the gas in that network. And once that model is there, we will be able to perform simulations with a whole set of values that you can change and the impact that will have on a network. And that's really important, not only for the network itself, but on something else before, for example, is the agreements with large customers that often get their energy, their gas directly from the main manager. Maybe they do want some hydrogen, and maybe they have some limitations on their equipment, not allowing them to have a certain percentage of dilution of the gas in their network. So the whole set of constraints that has impacts. Hydrogen will generate a lot of impacts, secondary impacts on the way of working of gas operators, and that's important to understand. Yeah, I think I reached the end of the presentation. I would really glad to reply some questions, and I see there have been a few.
Yes, thank you for your presentation, Geert. So maybe we'll start with the first question from Sebastian for you, Peter. What is the energy cost of liquefying hydrogen, and if it has an impact on the overall efficiency of this energy?
Yes, this is a very important question. Thank you very much. Allow me just to start with one other remark. Geert mentioned the Alstom trains, and in the Frankfurt area we will have a couple of them. I think the first is already in operation, and the trains, if you once have the opportunity to use such a train, it's a great experience because it's a different feeling to go in such a train compared to a whatever diesel engine what you have on tracks without overhead lines. So it's a great experience to go with such a train. But the liquefied hydrogen, of course, it's absolutely clear that liquefying hydrogen means to cool it down. This is needs a lot of energy, and so per definition, it's expensive. So it is, from my point of view, more a niche solution. And I see two options to use this niche. The first one is if I have a country that has an abundance of electricity like Iceland, and they use it to produce hydrogen, but how to get the hydrogen from Iceland to Europe? In this case, we should think about liquefying hydrogen. Talking about Europe, talking about Russia, talking about North Africa, I always would go for pipelines. This is much more economic compared to liquefying hydrogen. And once I have liquefied hydrogen, we should think about using it in the liquefied form, for example, as a fuel. When I think at the aircrafts that will be designed by Airbus, I would imagine that they will use liquefied hydrogen just to have because they don't have volume available. So the economic situation always has to consider the whole value chain. But again, liquefying needs energy, is expensive, and therefore will play a niche role. My opinion. If you agree, I also saw that Frédéric Arnaud asked a question about the interaction of H2 and CH4. That is also a very, very important issue. And the presentation of Geert clearly shows us that we have to understand this system. The considerations of our House of Energy, and we are working on a great demonstration project in the northern part of our federal state of Hesse, is that either we go for 100% hydrogen, and this we consider is the solution in the urban areas where we have buildings which still need a high temperature for heating, 60 degrees normally. And here we need some gas in order to get it. A heat pump will not work. It could be distributed heating, district heating, but we also think that we will need gas, and this could be 100% hydrogen. On the other side, in the more rural areas, there are a lot of gas-fired heating systems. And here we think we have to decarbonize this natural gas by adding hydrogen, and we think we should go up to 20%. The issue is that you have to exchange all the devices on the customer side when you go beyond 20%. But even if you change the content of hydrogen between 0 and 20%, this is a big challenge. And simulation tools, understanding the system, what's going on, how do you deal with one part of the grid where you have 10%, another you have at the same time 20%. These are big questions. We have to understand the mechanisms, and therefore I appreciate that Geert and his team are working on models and also on control systems, on prediction systems, to get such a very complex gas system, yes, under control, and but first of all to understand it much better. So in a nutshell, up to 20% would be the hybrid solution, 80% CH4, and the other would be go directly to 100% in the more urban area.
Thank you, Peter. Well, do we have any more questions? You can ask them on the question tag. And maybe in the meantime, I'm just going to give you the right answers for the polls. So the one with which percentage of hydrogen gas transporters feel comfortable with on their existing networks. The right answer was 2%. And for why is hydrogen difficult to mix in networks running at full capacity, the right answer, and most of you were right, is you need 3 times more gas volume to get the same energy. So I don't think we have any more questions.
Just to add, sorry, the 2% are the value that we have today, but we are heading to 20%. A lot of legislation, a lot of rules have to be changed, but the target is 20%. At the moment, we have 2%. Just for clarification, yeah.
Okay.
Yeah, I agree. Yeah.
Well, then thank you very much to all of you for being with us this morning. Thank you, Peter, for participating in the webinar as well. Thank you, Geert, for your presentation as well. You'll all receive an email with the follow-up information shortly. And thank you. Have a great day.
Thank you very much. Have a great day and nice weekend ahead.
Yep.
Bye-bye, everyone.
Bye.
Bye-bye.